Hello. In the previous video, we learned how to apply Lagrangian mechanics via simple free-fall examples. But the important question we must ask, why is Lagrange correct? And why does Euler-Lagrange work? Today, we're gonna prove that Lagrange is correct depending on our physical backgrounds and by applying three simple mechanical examples using Lagrangian mechanics. We will recheck the free fall example and take a look on two other examples, which are the simple harmonic motion of a string and the Coulomb's law. To recheck the free fall motion example, I will not repeat the steps of solution, but I will show the results directly. I remembered you that I solved this example step by step in the previous video, so check it please. We proved after several steps that my double dot plus mg equals 0. Now, by separating each term to a different side, we deduce that minus mg equals my double dot. Oops, minus mg is the projection of the weight force with respect to y-axis. So W equals ma, thus the force equals the mass times the acceleration, so F equals ma, which proves a previous formula we knew before, which is the formula of Newton's second law. Exciting. To deal with the second example about simple harmonic motion with a string, and knowing that the mechanical energy is conserved and the box has a motion on x-axis only, so the kinetic energy equals half mx dot, the potential energy equals half kx dot, then Lagrange, which is the difference between kinetic energy and potential energy, equals half mx dot squared minus half kx squared. Okay, now in order to apply Euler-Lagrange principle, we should find each term in its equation separately. So the partial derivative of Lagrange with respect to x dot is mx dot. The total derivative of mx dot with respect to time is mx double dot. The partial derivative of Lagrange with respect to x is minus kx. Now, substitute each needed term in the Euler-Lagrange equation. We get mx double dot plus kx equals to 0. So minus kx in the left side equals mx double dot in the right side. Oops, minus kx is the projection of the tension force with respect to x-axis. So the tension equals ma, and finally the force equals ma, which proves exactly the Newton's second law. Very exciting. The last example is about two charge systems, a large charge and a test charge separated by distance x from their centers. These two charges repel each other on x direction because their centers have no ordinates and because they have identical charge. Each charge is positive, so they must repel each other. The kinetic energy of the big charge is half mx dot squared. The potential energy of the big charge is equal to the work of the big charge, which is the tested charge multiplied by the potential of the big charge, which is Q small multiplied by K big Q over X. Now, the Lagrange, which is the difference between kinetic and potential energies, is half mx dot squared minus small q multiplied by k big Q over x. Okay, now in order to apply Euler-Lagrange principle again, we should find each term in its equation separately. So the partial derivative of Lagrange with respect to x dot is mx dot. The total derivative of mx dot is mx double dot. The partial derivative of Lagrange with respect to x is kq q small multiplied by k big Q over x squared, because the derivative of 1 over x is minus 1 over x squared, and minus minus will give me plus. Now substitute each term in its convenient place in the Euler-Lagrange equation. We get mx double dot minus q k big Q over x squared equals to 0. So mx double dot equals q k big Q over x squared. But we know that the force between the two charges is kq small multiplied by big Q over x squared, which is the Coulomb force. Then F equals ma, which proved for the third time that the Lagrange is correct and it's related to Newton's second law. Thank you for watching. We will solve more complicated problems in the next videos. So, to that time, stay, turn, and take care. Goodbye.